What did James Webb really see? Today, we embark on an extraordinary journey to the far reaches of the cosmos. In the infinity, where light takes more than 12 billion years to reach us, the James Webb Space Telescope has revealed the unthinkable, a gigantic spiral galaxy, perfectly ordered, that appeared when the universe was just a child. Its name, Zhúlóng, the torch dragon, a stellar colossus whose arms spiral with an elegance defying the accepted laws of galaxy formation. How could such a structure have emerged so early in a cosmos once thought to be still chaotic? And what if this galaxy, with its mass, shape, and stellar activity, challenged our most fundamental models? But this is only the beginning, because Zhúlóng is not alone. Other early spirals have been spotted. And what if, in their blazing arms, perhaps lies another deeper mystery, that of life? But before setting off on a new adventure, be sure to like the video and subscribe to the channel to not miss anything. Thank you, and have a nice trip. At the very beginning of April 2025, a team of scientists is methodically scrutinizing the data provided by the James Webb Space Telescope, often abbreviated as JWST. This space telescope, launched a few years earlier, aims to observe the distant universe with increased sensitivity compared to previous observatories. In this context, a study program called Panoramic has just begun its observation campaign of a specific region of the sky. The objective of this program is to uncover previously formed galaxies, or even spot unusual structures, to better understand how the universe organized itself in the first billion years after the Big Bang. In the files received on Earth, a surprising discovery lies in an area previously minimized by astronomers. A spiral galaxy, incredibly massive despite its young cosmic age, clearly appears in the images. This is how Zhúlóng was identified and suddenly captivated the scientific community. The name Zhúlóng was not chosen at random. In Chinese mythology, this term literally means torch dragon. The choice is symbolic. This galaxy seems to emit a powerful glow that travels an impressive 12.8 billion light-years before reaching the hypersensitive detectors of the telescope. It's always fascinating to realize that the light we observe today was born in incredibly distant eras. Indeed, when looking at the light from distant galaxies, we not only receive a light signal, but also travel back in time. Each photon that reaches us tells an ancient story. For Zhúlóng, it begins in a universe whose age was barely a few 100 million years after the Big Bang, making it a privileged witness of a still poorly understood period of cosmic evolution. The James Webb Space Telescope, meanwhile, is a true asset for examining such sources. Positioned at a Lagrange point nearly 1.5 million kilometers from Earth, on the opposite side of the Sun, it operates in stable thermal conditions. This helps it keep its instruments at very low temperatures, typically around 233 Celsius, which is essential for infrared observation. The telescope's optics, about 6.5 meters in diameter, collect the faint light of extremely distant objects. Among the JWST's operating modes is the NIRCam camera, used in the Panoramic program, capable of spotting fine details at infrared wavelengths, where these ancient galaxies shine more clearly due to the expansion of the universe. This expansion stretches the wavelength of light towards the red, a process astrophysicists call redshift. The measured redshift value for this galaxy is around 5.2. The redshift, noted as Z, quantifies the degree of stretching of the light emitted by the object. The larger Z is, the more distant the object is, and the further back in time we go. With a Z of about 5.2, it is estimated that the light from Zhúlóng took around 12.8 billion years to reach us. In other words, what we see of Zhúlóng is the image of the galaxy as it existed in its prime cosmic youth, less than 2 billion years after the Big Bang. This period covers the end of what is known as the epoch of reionization, an era during which the universe saw its first massive stars project energy back into a medium that was previously mainly filled with neutral hydrogen. Studying such a galaxy thus allows for a better understanding of how the first complex structures formed at a time when the universe was young and much denser than it is today. Images from the JWST show that its disk extends over about 60 to 62 kilolight years in diameter. Kilolight years corresponds to 1,000 light years, a light year being the distance traveled by light in 1 year, or nearly 10 trillion kilometers. Thus, a disk of 60 to 62,000 light years resembles more or less half the diameter of the Milky Way. Yet, the stellar mass of Zhúlóng, that is, the total mass of its added stars, is estimated to be about 10 to the 11th power solar masses. To put it in words, the galaxy contains approximately 100 billion times the mass of our Sun in terms of stars alone. This is considerable for such a distant, and by extension, young object in the chronology of the universe. This disproportion between the size of the disk and its stellar mass immediately draws reactions from specialists. Indeed, the Milky Way, which is twice as large in diameter, contains just over a few hundred billion stars, a comparable order of magnitude, but still more significant given its actual size. In Zhúlong's case, however, we have half of the usual galactic extent for a global mass, surprisingly close to that of our galaxy. This ratio suggests that the density of stars is particularly high in Zhúlong's disk. Astrophysicists then wonder whether this phenomenon is an indication of extremely rapid formation, or if this galaxy merged with other systems to inflate its stellar mass in record time during the early phase of cosmic history. Zhúlong's internal structure, as glimpsed in this first look, also shows the presence of a central bulge. In astronomical jargon, the term bulge describes the spheroidal, compact, and densely star-populated region located at the center of a spiral galaxy. Generally, an old bulge means that the stars found there are older and less active in terms of star formation. It is like a core that has already gone through several stages of evolution. The colors noted in the mid-infrared band indeed suggest that this bulge contains fairly old stars. The observation of star colors allows determining their approximate age. The older the stellar population is, the more its radiation, even shifted in the infrared, tends toward reddish tones. Researchers thus suspect that Zhúlóng formed a rather calm core relatively early before continuing to consolidate its disk. Nevertheless, this galaxy is not entirely dormant. Initial estimates reveal a star formation rate of about 66 solar masses per year. This means that each year, around 66 new stars of the Sun's mass, or a combined equivalent, are born in this galaxy. By comparison, the Milky Way in our time forms about 1 to 2 solar masses of stars per year. Thus, Zhúlóng is at a much higher level of stellar creation than our current galaxy. However, this pace is considered moderate in the context of galaxies in the distant universe, as some starburst galaxies can reach or exceed hundreds or even thousands of solar masses per year. But for a structured and well-ordered spiral galaxy, this figure of 66 solar masses per year is still an indication of sustained activity. In addition, the fact that Zhúlong's bulge already contains old stars while maintaining an active disk in terms of star creation is an indication that astronomers often describe as inside-out growth. In other words, it seems that the formation of this system began by concentrating matter in the central region, building the core or bulge very early, and then extended the stellar formation processes to the periphery, the outer regions of the galaxy. Observing both an aging core and a disk, still in full swing at redshift 5.2, is something remarkable that raises many questions. Classical models of galaxy evolution generally indicated that clearly drawn spiral disks did not appear so early in cosmic history, as they require some time to settle and to adjust the dynamics of stars and gas. Zhúlóng could thus evidence a faster scenario of galactic organization, and therefore reshape some cosmic evolution assumptions or simulations. To properly understand the measurement of stellar mass, it is important to know that astrophysicists often use the neighboring galaxy Andromeda or the Milky Way as a reference, both evaluated in the range of a few 100 billion solar masses. Researchers rely notably on a galaxy's overall luminosity, as well as the distribution of that luminosity according to wavelength, to deduce what type of stars and the total quantity of stars that may exist in this population. Slight uncertainties remain, because there are sometimes biases, for instance, in the estimation of dust, which can trap and re-emit light. In the case of Zhúlóng, astronomers have not yet found a strong presence of cold dust. If the dust is indeed rare, the light emitted by the galaxy's stars reaches the instruments more directly, thus facilitating the assessment of its total mass. Returning for a moment to the discovery of Zhúlóng allows for restoring the sense of wonder felt by the panoramic program team. Initially, the JWST data collection resembles a long mosaic of infrared images. These are fields that sometimes aim at particular targets, sometimes random areas for mapping. When scientists receive these images, specific objects selected by an automatic detection algorithm must then be identified. This algorithm detects, for example, packages of light of varying intensity, and based on their brightness variation by wavelength, determines whether it is a star, a galaxy, or an artifact, a simple detection flaw or a parasitic cosmic ray, for example. In the case of Zhúlóng, the software noted a luminous structure that, upon verification, did not correspond to a mere point, but showed a characteristic profile of an extended disk. A second look immediately confirmed the presence of a spiral shape. The fact that such a distant galaxy appears in such a harmonious form is surprising. This explains the researchers' fascination. Classical theoretical predictions about galaxy formation in a young universe often pointed toward more chaotic, irregular objects shaped by successive collisions. Yet, Zhúlóng already exhibits well-organized spiral arms, a well-defined center, and a stellar mass that exceeds computer simulations attempting to model the galaxy formation era. To understand precisely what is meant by a grand design spiral, it is first necessary to know that not all spiral galaxies are the same. Some, called flocculent spirals, have rather diffuse arms, sometimes broken or poorly defined. In the case of Zhúlóng, the spiral structure is much more regular. Two large arms are observed, almost symmetrical, gently wrapping around the galactic center. These arms form what are called density waves, which channel interstellar matter, gas, dust, and stars, into a harmonious and persistent pattern. In this scheme, imagine gravitational corridors where matter accumulates and reorganizes. It is this phenomenon that maintains the wavy shape of the arms, a bit like a roadway where cars, here stars and galactic gas, tend to group at the same places. This arrangement, often compared to that of a vinyl record whose grooves would be of higher density, gives Zhúlóng a striking and identifiable appearance, even in modern observation instruments. As we progress towards the center of this spiral, we discover a quiescent bulge, meaning a central bulge that houses, for the most part, old stars that are unlikely to form new stellar populations. In astrophysical language, quiescent generally means evolving slowly, with very few star births. The observation of the Zhúlóng bulge reveals that it is particularly reddened by the presence of old stars, likely formed at the very beginning of the galaxy's history. This reddish hue has a simple explanation. Older stars tend to emit less in blue and ultraviolet light, while they emit more in red or infrared light. When observing the central area with the instruments of the James Webb Space Telescope, the red dominance is striking, showing that the core is no longer the site of strong stellar creation activity. This aligns with the idea that this region is already aged. However, the galactic disk, the vast flat expanse surrounding this bulge, remains itself the scene of more sustained activity. Star nurseries in formation are detected here, relatively dense pockets of gas, and emissions that betray the existence of energetic processes. This teaches us a crucial lesson. The galaxy seems to have grown from the inside out, a concept researchers describe in English as inside-out growth. Concretely, the core formed first. It quickly reached maturity by depleting its gas, then the rest of the disk takes over later, continuing star production as the center settles into a more stable and older state. The fact that this growth occurs from the inside out, or inside out, can be seen in the distribution of stars and in their age. Scientists often work to determine the stellar populations of a galaxy by analyzing their light spectra or precise colors in different locations. If there are many young and hot stars, there will be more blue or ultraviolet light. And if, on the contrary, mostly old stars are found, they will be redder. In Zhúlong's case, the reading of the images taken by the James Webb Telescope's NIRCam clearly shows this color fracture, a rather red center and a more varied disk, which includes bluer areas. This chromatic disparity is not just visual. It reflects a past where the galaxy seems to have initiated its stellar formation early in its center, before extending its activity towards the periphery. As time passed, the gas concentrated in these external spiral arms, allowing the birth of new generations of stars more widely distributed in the disk, while the center, depleted of fresh gas, focused rather on maintaining already formed stars. However, perhaps the most impressive element of this morphology remains the galaxy's unusual performance in terms of converting baryonic matter into new stars. Baryonic matter refers to ordinary matter, made of protons, neutrons, and electrons, which is everything we consider visible matter, the stars, gases, dust, but also the matter that makes up our bodies or the planets. When we talk about baryon-to-star conversion efficiency, we refer to the proportion of this matter that, at any given time, manages to transform into stars. For most galaxies, especially in the young universe, this fraction remains modest because many factors oppose star formation: gas dispersion by stellar winds, supernovae, heating of the medium by the intense light of stars or active black holes, etc. In Zhúlong's case, estimates suggest that this conversion efficiency approaches 0.3. In other words, about 30% of the available baryonic matter is effectively converted into stars. This is a very high figure, especially for a time when the universe was only 1.5 to 2 billion years old. Astronomers still wonder how the galaxy achieved such a yield. To enhance the accuracy of these descriptions, scientists also study a crucial parameter, metallicity. In astrophysics, metallicity refers to the proportion of chemical elements heavier than hydrogen and helium within stars or gas. Heavy elements, such as carbon, oxygen, iron, silicon, and magnesium, mainly form in the cores of massive stars and are then dispersed during violent events like supernovae. The more generations of stars a galaxy has experienced, the more heavy elements it accumulates. Therefore, metallicity is an indicator of a galaxy's chemical evolution degree. The higher the metallicity, the more time the galaxy has had to enrich its interstellar medium with metals. For Zhúlóng, the photometry conducted by the JWST shows a higher metallicity than expected for such a young object in the universe's history. Infrared filters are often used, capable of discerning the light emitted by certain compounds or absorption lines corresponding to gases richer in metals. Astrophysicists then model the energy curve that corresponds to each wavelength, which is known as SED photometry, spectral energy distribution. By comparing these data to stellar population models, one can estimate the metal content, and thus the galaxy's metallicity. Where there is a certain curiosity is the noticeable absence of cold dust, which remains unconfirmed for the moment by ALMA. ALMA is a network of radio antennas positioned atop the Chajnantor Plateau in northern Chile, over 5,000 meters above sea level. Thanks to its observations in the millimeter and submillimeter domains, ALMA is unrivaled in detecting cold dust and molecular gas, often trapped in giant clouds of molecular hydrogen. Initial measurements suggest there might be less cold dust than expected in Zhúlong's disk. Cold dust is that which would be at temperatures often below 250 degrees Celsius or even more frigid, emitting most of its radiation in millimeter or submillimeter waves. Ordinarily, in galaxies intensely forming stars, one expects to find cold dust accompanying nebulae and gas clouds. Yet, in this early galaxy, either it hides and remains undetected with current instruments, or it is genuinely less abundant. Future observations aiming to precisely measure luminosity at submillimeter wavelengths will determine if this paucity of dust is real or just currently invisible. If the absence of cold dust proves to be confirmed, it would mean that Zhúlóng converts its gas into stars more directly and cleanly, quickly expending available resources without forming large-scale dusty reservoirs. The discovery of Zhúlóng has sent a true shockwave through the scientific community, both for its unexpected nature and the significance of its implications. To fully appreciate why this revelation was labeled a coup de théâtre, it is necessary to first revisit the theoretical context prevailing before 2025. The image processing procedure used in the panoramic program was relatively conventional in principle, although pushed to unprecedented levels of performance. The process began by pointing the telescope toward a region of the sky chosen for its low density of foreground stars to minimize the glare from potential sources close to the Milky Way. NIRCam then captured infrared light in multiple bands, each sensitive to different wavelengths, to distinguish stars, gas, and other galactic components. The raw data from several hours of observation were stored in batches and subsequently sent to ground-based analysis servers. Once received, these files went through an automatic detection and classification algorithm trained to recognize different galaxy shapes. This algorithm, based on deep neural networks, offered an initial descriptive label such as diffuse spheroid or flat disk, based on the overall morphology viewed in the images. For most astronomers, this identification process is a considerable aid. On a scale of millions of objects, it is nearly impossible to check everything manually. However, the weak point of any algorithm remains its margin of error, especially when it encounters rare or unexpected cases. Moreover, when an automatic classification system has seen only a limited number of examples of very distant spiral galaxies, or none at all, it sometimes struggles to correctly recognize these silhouettes. This is precisely what happened with Zhúlóng. On the first pass, the machine hesitated between elliptical galaxy and irregular galaxy. For it, the presence of a reddish bulge combined with a possible embryo of arms, but not clear enough to declare a complete spiral pattern. The object was therefore set aside in a manual verification category for further examination. It was at this point that a ground team, composed of astronomers and engineers, was tasked with reviewing the image more precisely. The discovery took place during a routine quality check, conducted by a group led by researcher Mengyuan Xiao. Her role was to go through a batch of images marked as ambiguous to decide whether to refine the algorithm, relabel the data, or conduct a new observation for confirmation. During an apparently uneventful evening of work, Mengyuan scrolled through a large number of thumbnails, reviewing objects whose shape was not clearly identified by artificial intelligence. Suddenly, she stumbled upon a slightly blurry snapshot, where she thought she distinguished two very thin arms wrapped around a brighter core. Interested, she applied different contrast filters to reveal more details. The arms, almost unbound, then became clearer. She immediately realized that this symmetry clearly evoked a spiral pattern. Better still, the emerging spiral seemed remarkably well organized, in a way that one would usually associate with much more mature and recent galaxies in cosmic history. At that moment, a mix of excitement and disbelief gripped the team. The analysis protocol nevertheless imposed a certain prudence. Before declaring victory, it was necessary to check that it was not an instrumental artifact, a fortuitous superposition of several galaxies, or a disturbance occurring during calibration. Mengyuan Xiao and her colleagues then undertook to validate the discovery using other available observations. They started by searching for confirmation in images from other infrared filters. One of these filters, sensitive to slightly shorter wavelengths, showed that the spiral structure persisted, confirming that it was not simply due to a light halo or electronic noise. Faced with these preliminary indications, the team realized they were potentially looking at one of the most distant spiral galaxies ever detected. The very red central bulge suggested an already aged core, while the arms surrounding this core hinted at a still active star-forming disk. Cross-checks took place. Other observation programs, conducted by various instruments, confirmed the presence of a light source in the same spot in the sky. Doubts quickly vanished. In just a few days, the group gathered enough evidence to announce that a massive and coherent spiral structure had just been spotted, where no one expected such a thing at this cosmic time. This result is all the more surprising given that, according to commonly accepted models, the establishment of spiral arms requires a certain degree of dynamic maturity. Galaxies are supposed, in principle, to have rotated sufficiently on themselves to establish stable density waves, those famous zones where matter tends to accumulate in spiral patterns. Yet, less than 2 billion years after the Big Bang, it was assumed that differential rotation had not yet been well established in most galactic systems. Moreover, the formation of a thin disk, a crucial condition for having a well-drawn spiral, generally requires prolonged time for the gas to cool and spread out in the form of a flattened galactic plane. And yet, Zhúlóng proved that this scenario did not apply to all cases, or that there could be faster consolidation pathways than those admitted until now. As rumors of the existence of such an early spiral spread, the scientific community organized to obtain other types of data. In particular, confirming differential rotation represents a key objective to unambiguously validate the status of a grand design spiral. The concept of differential rotation means that the material of the galaxy, at different distances from the center, rotates at distinct speeds and periods. It is precisely this phenomenon that gives rise to spiral arms by creating zones where the matter is denser. In an elliptical or irregular galaxy, the distribution of speeds is more chaotic, and this type of ordered and repetitive structure is not observed. To untangle the dynamic behavior of Zhúlóng, astronomers are eager to use high-resolution spectra capable of measuring the internal movements of gas and stars. Two instruments have been considered to provide these crucial observations. The first is NIRSpec, the near-infrared spectrograph. Also installed aboard the James Webb Space Telescope, this spectrograph can study the light from the galaxy in detail and break it down according to its different wavelengths. By measuring fine variations in the emission or absorption lines, the rotation speed of the gas can be determined. This gas, composed mainly of hydrogen as well as other heavier elements created by the stars, collectively referred to as metals in astrophysics, emits specific signatures. When a modern shift of these signatures is observed, potential movements of recession or approach along the line of sight are detected. By combining measurements taken from different points of the galaxy, its complete kinematics can be reconstructed, and it can be seen if the stars or gas clouds follow a pattern consistent with differential rotation. The second essential instrument is ALMA, a network of 66 radio antennas installed on the Chajnantor Plateau, more than 5,000 meters above sea level in northern Chile. ALMA scans the sky in millimeter and submillimeter wavelengths, allowing it to detect the presence of molecules such as carbon monoxide in interstellar gas clouds. The emission lines of this carbon monoxide provide information about the mass and velocities of the rotating gases. Thus, the crucial importance of these complementary observations is understood. If NIRSpec and ALMA confirm that the galaxy rotates like a mature spiral, we will be able to state unequivocally that Zhúlóng is indeed a complete spiral disk, and not just a disk beginning to organize itself or a hybrid object that doesn't fit recognized typologies. Already, simulations based on NIRCam images suggest that the stellar mass of Zhúlóng is exceptionally high for the era, reinforcing the idea that it may have assembled in an unusual manner, perhaps through very efficient gas accretion or a particularly well-aligned merger with one or more protodisks. In any case, for the community, this discovery is considered a key milestone, as it shatters the hypothesis that galaxies would still rotate confusingly at this stage of cosmic history. Even before obtaining the first spectra, the mere existence of well-defined arms in such a young universe already raised fundamental questions. How does a galaxy manage to stabilize a thick disk in such a short time? What exact role does dark matter play, these still unidentified particles that, according to models, constitute a large part of the galactic mass? Is the spiral structure induced by gravitational interaction with another neighboring object, or does it result from an internal phenomenon within the dark matter halo and the primordial gas turbulences? These are points to clarify to refine our scenarios of galactic formation. In this puzzle, differential rotation is a key piece. If a consistent velocity gradient in the radial direction is detected, meaning that the velocity decreases or increases progressively as one moves away from the center, then it signifies a characteristic signature of a spiral. Elliptical galaxies, for their part, may display overall rotation, but they do not exhibit this persistent spiral and distinctly cut arms. Irregular galaxies, on the other hand, will have less ordered movements and asymmetrical or fragmented structures. Thus, the spectral confirmation of the dynamic appearance of Zhúlóng is the next step to solidify the discovery. The data collected by the NIRSpec spectrograph will also allow for the measurement of key emission lines, such as those of ionized oxygen or hydrogen. These spectral lines provide clues about the rate of star formation. The higher this rate, the more ionized hydrogen is observed, which forms in hot regions around massive and luminous stars. Similarly, the presence of oxygen emissions indicates the degree of heating and ionization of the interstellar medium. Understanding these mechanisms is crucial, not only for evaluating the shape of Zhúlóng, but also its physical properties, star formation, gas density, metallicity, etc. On the ALMA side, the essential step will be to detect carbon monoxide lines. At these millimeter wavelengths, a redshift of 5.2 shifts the CO6-5 line into a longer wave range than in the laboratory on Earth. Nevertheless, thanks to ALMA's antenna configuration, we can measure Doppler shifts corresponding to radial velocities within the galaxy. Velocity maps will be obtained, sliced into wavelength channels. These maps will reveal how the molecular gas moves from one arm to another, and whether this movement is consistent with spiral rotation or possible disturbances. If the arms are well defined, we expect speed distribution patterns that highlight the gradual winding of the disk. In other words, an arm will gain or lose speed, depending on its relative position to the center. In the months following the discovery, initial assessments have been made on the likelihood that Zhúlóng corresponds exactly to an orderly spiral. There is a small uncertainty due to the fact that despite the impressive resolution of NIRCam, all details at such high redshifts are never discerned. Some researchers remain cautious and prefer to refer to a candidate spiral pending spectral confirmations. However, judging by the sharpness of the arms and the constitution of the central bulge, everything points to a true spiral disk. This discovery prompts us to question, or at least revise, our interpretations of how galaxies were constructed when the universe was still very young. In classical theories, it was assumed that early formed galaxies resulted from vigorous collisions. Dark matter halos would then assemble around potential wells, attracting large amounts of hot gas and small blocks of burgeoning proto-galaxies. This would have created a chaotic environment, not conducive to the emergence of orderly disks. Researchers often refer to chaotic models of the young universe, in which spiral galaxies form later, when disturbances have calmed enough to let the disks stabilize. Indeed, in a galactic disk, the matter must orbit in a relatively regular manner, with overall speeds that are rather coherent. It is therefore surprising to see that barely a billion years after the Big Bang, such a level of organization already exists. To explain such a structure, several avenues open up. The first, often called cold accretion, suggests that in certain regions of the universe, intergalactic gas could have flowed along immense filaments, providing a continuous supply of fresh gas that had not yet been too heated. The term cold here does not necessarily mean only a few degrees above absolute zero, but indicates that the gas is less hot than would be imagined in a model where it is heavily shocked and compressed during countless collisions. In this scenario, if the gas flows smoothly without creating too much chaos, it can gradually organize into a flattened disk. The angular momentum, i.e., the mechanical property related to the speed of rotation and the mass of the matter, is much better conserved when the gas is not overly shaken. This cold accretion could allow for the formation of stable disks within the first billion years, contradicting the idea that everything must be violent upheavals. In addition to the cold accretion hypothesis, another possibility sometimes suggested by astrophysicists involves the gentle merging of pre-aligned disks. In this case, it is assumed that two or more small disk galaxies, already roughly aligned on the same plane, come into contact in a relatively peaceful manner. Instead of frontal or oblique collisions leading to chaotic clusters, their meeting occurs at slower speeds, following similar trajectories. This moderate merging would then give rise to a larger disk-shaped galaxy, quickly adopting a spiral pattern if the conditions of density and rotation are conducive. The idea is that since these small disks do not arrive randomly, but in an almost coordinated configuration, the global effect results in the continuity of rotation and the preservation of a spiral structure. Although this hypothesis does not yet have unanimous support, it is increasingly being put forward to explain the rapid growth of large spiral galaxies in the early cosmic times. Beyond merely challenging the chaotic vision of a young universe, the discovery of Zhúlóng also raises the crucial issue of cosmic reionization. Reionization is the period during which the neutral gas pervading the universe, mainly hydrogen, was gradually ionized by the energetic light from various sources, primarily massive stars and active black holes like quasars. To briefly recap what this is about, after the Big Bang, the universe was very hot and ionized. Then, as it cooled, allowed the recombination of matter, or recombination, around 380,000 years. At this stage, hydrogen and helium nuclei captured their electrons, creating a mainly neutral medium. This is also the period when the cosmic microwave background, this fossil light observable even today, formed. After this moment, the universe becomes somewhat dark, because there are not yet enough luminous structures to shine and illuminate the cosmos. This period is called the Dark Ages, which spans roughly from 380,000 years to 200 million years after the Big Bang. Then, as the first population 3 stars, the very first stars extremely metal-poor, meaning lacking elements heavier than helium, formed, ultraviolet light began to flood space. Emerging galaxies, especially those populated by massive stars, then contributed to ionizing the surrounding hydrogen again. This phase is called reionization and roughly covers the period from 200 million years to about 1 billion years after the Big Bang, although there is still debate about the exact end date of this process. During this period, highly energetic ultraviolet photons are emitted in large quantities and tear apart the hydrogen atoms, stripping away their electrons, thereby transforming the surrounding gas into ionized plasma. In the classical scenario, it was thought that small galaxies, full of gigantic stars, played a decisive role. However, if massive spirals like Zhúlóng already existed, they might have acted as real UV photon factories, thanks to potentially high star formation rates in their disks. The reasoning is as follows. If a massive spiral galaxy develops multiple star-forming regions rich in hot and massive stars, it can release enormous quantities of ultraviolet photons into the intergalactic medium. These energetic photons, as they diffuse out of the galaxy, ionize the surrounding hydrogen. The cumulative impact of many such galaxies could thus accelerate or enhance reionization, modifying the usual timeline considered. Astronomers then wonder if the presence, and therefore the influence, of significant disk galaxies in these distant epochs has not been underestimated. However, the question remains complex. It needs to be confirmed whether these massive spiral galaxies actually let enough ultraviolet photons escape, or if their internal gas and dust do not capture a significant portion of the light. Indeed, dust can absorb UV radiation and then re-emit it in other wavelengths, thus limiting the direct contribution to reionization. In the case of Zhúlóng, initial estimates suggest a relative scarcity of cold dust, which would support the hypothesis of a good leakage of UV photons. Between 200 million and 1 billion years after the Big Bang, reionization took place, a crucial phase where most astrophysicists agree that large galactic structures began to form. It is also during this time frame that the appearance of Zhúlóng, among other massive galaxies, occurs. The data from the JWST seem to indicate that the formation of significant galaxies with already complex organization, like a spiral, sometimes occurs earlier than our previous models predicted. Finally, after 1 billion years and up to the present, the universe continues to expand and structure itself. Galaxies consolidate, merge, form galactic clusters, and a peak in star formation is observed between 2 and 3 billion years after the Big Bang, before experiencing a slow decline, a phenomenon known as galactic downsizing. Massive galaxies begin to form fewer stars, while smaller galaxies continue to grow at their scale. The reassessment of theoretical frameworks related to the early stages of galactic formation is therefore multifaceted. First, the presence of an organized galaxy so early suggests that not all sectors of the universe were as chaotic as once believed. There might have been relatively calm environments, allowing for orderly structural growth. Secondly, these early spiral galaxies, if numerous, and future observations from the JWST or other next-generation telescopes, like the extremely large telescope, could confirm this, might have contributed significantly to reionization. Thirdly, the very observation of these types of galaxies compels us to better understand the internal dynamics of high redshift disks. If gas, dust, and stars are already organized in differential rotation, meaning internal parts rotate faster than external parts, it indicates that matter has had time to settle and equilibrate in a coherent manner. This factor can only occur with specific mechanisms of energy dissipation, redistribution of angular momentum, and regulation of star formation. Cutting-edge numerical simulations, like illustrious TNG or other cosmological modeling programs, will need to be refined to reproduce these conditions, lest they fail to model well-defined disk formations. The investigation of these galaxies could challenge the very idea that the formation period of most large structures is so late. We know that our own Milky Way, which is also a spiral galaxy, took several billion years to develop its current configuration: central bulge, spiral arms, halo of ancient stars. But this does not exclude the possibility that some galaxies may have taken a faster path if the physical conditions and distribution of matter were favorable. Astrophysicists often use the term inside out to describe the growth of a galaxy from its central bulge to its outer regions as gas settles and stars form in the disk. Zhúlóng already appears to have a quiescent bulge, meaning a core of older stars less inclined to form new stars, and a disk still actively forming. This configuration, not only spectacular, conflicts with the idea that the young universe was too violent to allow for such well-organized structures. We will now provide an overview of several pioneering spiral galaxies, sometimes referred to as improbable galaxies for this cosmic youth. Let's begin our journey with CEERS 212, nicknamed Baby Whirlpool by the research team that contributed to its discovery. CEERS stands for Cosmic Evolution Early Release Science Survey. It is a program designed to exploit the capabilities of the James Webb Space Telescope from its earliest observation phases. The goal of SEERS is to scrutinize areas of the sky already well studied by other instruments to compare and complement our data in more detail. The galaxy SEERS 2212 is located at a redshift of about 4, or slightly more according to the latest estimates. This value places its light as having traveled for approximately 12 billion years. By looking at SEERS 2112, we see it as it was when the universe was still a young space of about 1.8 billion years old. Why is it called Baby Whirlpool? Simply because it resembles the great galaxy M51, nicknamed the Whirlpool Galaxy, located much closer to us, at only about 30 million light-years away in the constellation Canes Venatici. The resemblance is striking. SEERS 2112 displays well-defined spiral arms, revealed by the very precise imaging of the JWST. What is particularly astonishing is the apparent homogeneity of its arms and the already detectable presence of star-forming regions. Astronomers have been able to measure, via the photometry of its light, a stellar mass that is beginning to reach several tens of billions of times the mass of the Sun. Of course, this estimate is still subject to uncertainties. As the further back we look in time, the more complex it becomes to distinguish the signal due to stars from that due to possible interstellar dust or other factors. The galaxy SEERS 2112 has caught the attention of researchers because it hints at an already mature spiral structure, suggesting a relatively calm formation process, or at least less chaotic than expected for this cosmic era. It is imagined that it could have taken the shape of a disk consolidating smoothly with a continuous supply of gas through cosmic filaments. These filaments are long structures of matter in which gravity channeled gas towards the proto-galaxies. SEERS 2112 could thus have grown progressively without too many head-on collisions with other galaxies of similar size. This is a very instructive scenario for understanding how large spiral disks were forged in the youth of the universe. Let's continue our exploration with another celebrity of the distant sky, SPT-041847. This name actually hides an acronym. SPT refers to the South Pole Telescope, an observatory set up at the South Pole, designed in particular to study the cosmic microwave background and conduct surveys of distant galaxies. The galaxy SPT-041847 was detected thanks to the gravitational lensing effect. In simple terms, when a massive object, often another galaxy or a cluster of galaxies, is located along the line of sight between an extremely distant galaxy and Earth, the strong gravity of the intermediate object can bend the light of the background galaxy. This produces a natural magnification, as if the distant galaxy were observed through a cosmic magnifying glass. This phenomenon was predicted by Albert Einstein's theory of general relativity, which describes how mass curves space-time. This galaxy thus appeared to us as an almost perfect ring, sometimes called an Einstein ring, in the radio and submillimeter data, obtained notably by the ALMA radio telescope array. This allowed researchers to reconstruct the undistorted image of the background galaxy, and, to their surprise, it presents a compact and regular disk with a structure close to a spiral and an already formed central bulge. Once again, we are facing a true challenge to our models, as this regularity, this well-organized disk, and this bulge in place at such an early time indicate that the galaxy structured itself rapidly. Located at a redshift of about 4.2, the galaxy dates from a period in the universe when it was around 1.5 to 1.6 billion years old, according to the cosmological calibration adopted. This is relatively close to Sears 2112 in terms of era, but this galaxy has sparked even more astonishment among specialists because we can discern a very high stellar mass as well as a star formation rate that seems quite dynamic. We are talking about a few tens of solar masses formed per year, or even more, which, for such a young galaxy, is considerable. Moreover, the fact that detection relies on sub-millimeter wavelengths has allowed measurements of emissions from interstellar dust, as well as molecules like carbon monoxide, which often accompany star formation sites. Some of these molecular lines have helped determine the rotational dynamics of this galaxy's disk, showing that it already rotates like a mature galaxy with a massive central core. It's an exciting puzzle. How did such order establish itself so early in cosmic history? Researchers hypothesize that the galaxy may have benefited from a rapid influx of fresh gas from the intergalactic environment, or from one or several relatively gentle mergers with other small pre-aligned disks. The main hypothesis is that of cold accretion, rapidly channeled into a dark matter halo, allowing the galaxy to take shape without being too disturbed. Let us conclude this overview with the galaxy nicknamed the Big Wheel, observed by JWST at a redshift nearing 3, which corresponds to nearly 2 billion years after the Big Bang. Although this galaxy is a bit less extreme in terms of remoteness than the previous two, it remains remarkable for its massive spiral appearance and dimensions. In the universe's history, Zebra 3 is still a young age, even if it is after the era of reionization, the period during which the universe transitioned from a neutral to an ionized medium under the action of the first stars and galaxies. The peculiarity of the Big Wheel lies in the width of its disk and its abundance of already formed stars. Photometric surveys, complemented by spectroscopic estimates, show that this galaxy could have a stellar mass significantly greater than that of the Milky Way of today, yet over 13 billion years old. Moreover, JWST images clearly show marked arms, likely maintained by density waves, which astrophysicists sometimes call quasi-stationary spiral waves. This pinnacle of spiral structure reveals a very organized dynamic already, a rotating gas disk, more or less in equilibrium within the dark matter halo, with a radial density distribution that maintains the spiral form over time. From a scientific point of view, the interest in observing the Big Wheel is combined with that of comparing it to other spirals of the early universe. Astronomers wish to understand if the formation laws of past spiral galaxies follow the same rules as those that shaped great local spirals like the Milky Way or the Andromeda galaxy. Initial data indicate, again, a relatively neat disk, without major signs of recent merger. All this nurtures the idea that some galaxies manage to assemble and organize themselves much faster than old hierarchical cosmology models suggested. By compiling data from these 3 galaxies and other objects still under study, astronomers identify several trends. The first is the increasing rarity of well-organized spiral galaxies at redshifts above 3. To better understand, it must be noted that many galaxies detected in the early universe appear chaotic, irregular, or in the throes of merging. Grand design spirals are apparently exceptional. They were thought to be almost non-existent in the time window from 500 million to 1 billion years after the Big Bang. Yet, the discoveries previously discussed modify this landscape. These galaxies embody a challenge. Their existence suggests that there are more serene formation pathways, without titanic collisions, or mechanisms where star formation and spiral organization occur very rapidly. The second trend is the need to consider the observation bias. In other words, our ability to spot these distant spiral galaxies heavily depends on the power and sensitivity of our instruments. When we detect a spiral at Z3, there are likely many others that elude us, either because they are less luminous or because they are shrouded in thick clouds of dust. The JWST, with its infrared instruments, is far more capable of precisely probing the radiation emitted by newborn stars, even if they are hidden behind dust. This means that spirals might have existed before, but they simply remained invisible to less sensitive telescopes. Furthermore, when we shift in frequency towards submillimeter or millimeter waves via ALMA, we can also detect the signatures of molecules in dust. The case of SPT-Z418-47 wonderfully illustrates this complementarity. We would not have perceived it so clearly without the gravitational lensing effect combined with the sensitivity of the ALMA network. The third trend concerns the power of the JWST. Since its launch in December 2021 and its deployment in orbit around the Lagrange point L2, this space telescope has revolutionized our observation capabilities in the near and mid-infrared. Thanks to its large collecting surface and the quality of its instruments, it can discern structural details inaccessible to Hubble on galaxies at very high redshift. It also provides more precise spectra, revealing the chemical composition, rotational kinematics, and metallicity. In other words, the proportion of elements heavier than hydrogen and helium in the star. Only a telescope of this magnitude could unveil the fineness of distant galaxy arms or the cohesion of the big wheel disk. Considering all these discoveries, a fundamental hypothesis can be drawn. The presence of substantial spiral disks within the first billion years could indicate a variety of galaxy formation rates. In other words, not all galaxies would have been involved in epoch collisions or massive instabilities. There would have been relatively calm niches where disks could flourish and organize with a moderate rate of disturbances. This scenario contradicts the simplistic idea of an initially violent and chaotic universe. Nevertheless, we must not fall into the opposite extreme. Spiral galaxies in the primordial universe remain rare, as current catalogs show. There are many more irregular galaxies, or those dominated by intense, dispersed star formation activity. But these rare objects are essential for understanding cosmic processes. They allow testing models of cosmic structure and understanding the distribution of dark matter, halo dynamics, the impact of minor mergers, and cold gas flows. They also serve to compare the formation chronology of central bulges, a critical component for the long-term stability of a spiral galaxy. But then, how is a spiral galaxy really built? Imagine a vast cosmic ocean filled with gas and dark matter in which a rotating disk gradually forms. At first glance, this may seem almost poetic, but the physical mechanisms at work are quite real. To fully grasp this process, one must break down each step and understand why, after several 100 million years, we not only get a disk, but also those elegant spiral arms. To understand why most spiral galaxies are organized into flat disks, we need to look at the conservation of angular momentum. Angular momentum is defined as the quantity that describes the rotation of an object. When a gaseous mass contracts under the influence of gravity, its angular momentum is globally conserved. as the primordial cloud shrinks, it must rotate faster, much like a figure skater pulling in her arms to spin faster. In the galactic context, this initial cloud contains not only so-called baryonic particles, ordinary gas and dust, but also dark matter, invisible to us, which is indirectly detected through its gravitational effects. The formation of a thin disk results from the fact that most of the matter rotates around a central axis, somewhat like a vortex. Baryons, which are more sensitive to friction and energy exchanges, eventually flatten into a disk. On the other hand, dark matter particles, which only interact weakly with each other, except through gravitational force, remain more diffusely distributed in a spherical halo encompassing the entire galaxy. This halo acts as a sort of framework, attracting matter and stabilizing the system's rotation. As soon as the rotational speed sets in, the gases begin to spread out and form a disk with varying thickness. This is known as thin disk physics, a delicate balance between centrifugal forces, gravity, and gas pressure. Once a disk is well established, it remains to explain what creates and maintains these spiral arms. In early hypotheses, it was thought that the arms were merely concentrations of gas and stars, moving at the same speed as the disk. But if that were the case, one would expect these arms to inevitably twist and disappear after a few galactic rotations. However, in reality, we observe persistent spirals that survive for hundreds of millions of years. Two major families of models have been proposed to explain this apparent stability. The first is the quasi-stationary density wave model. Here, the idea is that there is a density wave moving through the disk, much like a wave moving across the surface of water. If you imagine a raft on the sea, the wave passes under the raft, which rises and then falls, but the wave crest continues its journey. Similarly, stars pass through these density crests, compressing locally and triggering new star formations in denser regions. Although the stars themselves move, the general structure of the spiral, carried by the density wave, remains relatively stable. The second approach, called swing amplification, highlights a mechanism of amplification related to the differential rotation of the disk. In a galaxy, the inner parts rotate faster than the outer regions. If a slight perturbation occurs, it can be stretched and swept by the rotation, thus amplifying the density variations in certain areas. This shearing amplification strengthens the arms, much like a mechanical arm, a kind of lever, magnifying an initial signal. The existence of such phenomena allows the arms to appear, intensify, and sometimes fade, while giving the illusion of a quasi-permanent structure when the galaxy is observed at a given moment. In many spiral galaxies, one sometimes notices the presence of a bar at the center, a linear concentration of stars stretching from one side of the nucleus to the other. This bar acts like a cosmic skater, transferring angular momentum to different radii within the disk. In practice, the bar can emerge from small internal asymmetries. Once the bar instability sets in, it extends and intensifies, substantially redistributing matter. In this context, the term Lindblad resonances is often used. Resonances are specific frequencies at which the motion of stars synchronizes with that of the bar or density waves. Simply put, it's a bit like when a swing starts to oscillate more and more if you push at the right moment. Lindblad resonances, inner or outer, correspond to points in the disk where the orbital motions of stars align with those of the bar or the spiral pattern. Result: the resonance can concentrate matter in certain regions, potentially including between the bar and the arms, or even beyond. This dynamic plays a role in the radial migration of stars. Under the effect of resonances, stars can move over great distances within the disk, either towards the center or towards the periphery. At first glance, one might imagine a static disk where each star orbits around the center and remains at the same distance, but the reality is more complex. In a barred spiral, some stars get trapped in these resonances and gradually migrate. This radial migration affects the distribution of metals, meaning elements heavier than hydrogen and helium, and it also alters the distribution of stellar populations throughout the galaxy. In the universe, galaxies do not evolve in isolation. They are part of a gigantic web of structures called the cosmic web, made of filaments of gas, dark matter, and halos that stretch over scales of several 100 million light-years. The disk of a spiral galaxy like Zhúlóng, or like our Milky Way, can be perturbed by these exchanges with the environment. When two galaxies pass relatively close to each other, a tidal shear occurs. The difference in gravity from one point to another in the galaxy undergoes forces that can stretch or twist the shape of the disk. This tidal phenomenon can sometimes trigger bursts of star formation, alter the shape of the spiral arms, or even reinforce them. Besides these interactions, it is known that spiral galaxies can draw in matter along cosmic filaments. These filaments form a network, like arteries, where gas slowly flows towards the potential wells that are the galactic halos. This process, known as cold gas accretion, is essential for the continued formation of stars over time. When a denser gas stream falls onto the disk at high speeds, it can easily drop to extremely low temperatures, around a few dozen degrees above absolute zero, that is about 250 JWST, before mixing with the existing matter. By adding to the disk, this gas fuels new clouds, which in turn can spawn star clusters. Thus, the cosmic environment is not just a distant backdrop. It can literally shape the spiral structure, affect the intensity of the arms, and influence the pace of star birth. This perpetual reorganization also influences the chemical diversity of a disk. Dense regions in the arms favor the genesis of massive stars, which will heat their surroundings and eventually explode as supernovae, thus ejecting heavy metals, iron, nickel, uranium, and others, into the interstellar medium. These metals then mix with the neighboring gas, which will form new generations of stars. Over the rotations, these elements enrich different parts of the disk, notably thanks to the mechanisms of radial migration that move stars and gas around. So, the magnificent spiral is not merely an aesthetic pattern, it's a real chemical factory, producing metals and redistributing matter over vast distances. What appears to be a neat drawing and arms carved into perfectly designed whorls turns out, on the scale of 1,000,000 years, to be a constantly moving phenomenon. Stars are born, live, and die, and their energy modifies the pressure of the surrounding gas. The heated gas bubbles can reach temperatures of several tens of millions of degrees before cooling down by emitting radiation. Colder zones, at 263 JWST for instance, allow the condensation of more complex molecules, carbon monoxide, formaldehyde, which favor the emergence of new dense clouds and eventually new stars. Spiral arms are thus nourished by a form of perpetual regeneration, woven from feedback loops between star formation, environmental heating, and the density wave that girdles the galaxy. Since the beginning of the 20th century, astronomers have been trying to understand the morphological diversity of galaxies. Edwin Hubble, an American astronomer, played a crucial role in this endeavor by proposing a classification known as the Hubble sequence. At the time, knowledge was limited, mainly based on visible light photography. Hubble had observed nebulous objects, sometimes elliptical, others showing spiral arms, and yet others not corresponding to any regular shape. To organize this vast variety, he created a scheme visually represented by a sort of two-branched tuning fork. On the left of the tuning fork, we find elliptical galaxies, classified from E0, almost spherical, to E7, more flattened. On the right, the branches divide into ordinary spirals, noted as S, like say, SB, CC, etc., and barred spirals, noted as SB. Lenticular galaxies, noted as 0, on the other hand, are positioned at the bifurcation point between the elliptical branch and the spiral one. This point serves as a pivot, as it is generally estimated that lenticulars exhibit characteristics halfway between ellipticals, no marked spiral arms, rather smooth appearance, and spirals, the presence of a disk. Finally, some galaxies, too chaotic to fit a specific type, are described as irregular, letters IR or sometimes IM, for Magellanic irregulars. Elliptical galaxies, often abbreviated to E, represent the simplest and oldest apparent form in Hubble's classification. They are generally distinguished by an oval appearance without discernible spiral arms. At first glance, they seem to contain only old stars, since most young blue stars, a sign of intense star formation, are absent or very rare. In terms of composition, ellipticals are often rich in stars from older populations, having a high content of heavy elements. The passive nature of ellipticals is partly explained by the fact that interstellar gas, the raw material for star formation, is often poor or insufficient to spark new starbirth centers. When encountered, it is frequently hot, at temperatures of tens of millions of degrees, a temperature so high that it prevents condensation into dense clouds. Thus, ellipticals prove to be minimally conducive to the continuous creation of new generations of stars. In astrophysics jargon, they are often referred to as quiescent galaxies, meaning they are minimally or not active in terms of star formation. At the other end of the morphological spectrum, we find irregular galaxies, designated by IR. Generally, they do not display a clear central bulge, clearly defined spiral arms, or even apparent symmetry. Their shape is asymmetric, sometimes twisted, often disrupted by external gravitational forces, such as the influence of a more massive neighboring galaxy. The Magellanic Clouds, which orbit our galaxy, the Milky Way, are famous examples, known since antiquity in the southern hemisphere. Irregular galaxies can, in some cases, be rich in gas and dust, with many bright star nurseries. In fact, some irregular galaxies are particularly active in terms of star formation, creating clusters of stars at a furious pace. Others, conversely, seem devoid of a gas reservoir, or their gas is partially expelled by stellar winds or supernovae. These chaotic entities provide a fertile ground for studying the physics of interstellar turbulence and tidal interactions, all of which can drastically reshape the appearance of a galaxy. As we progress in the traditional Hubble sequence, we reach a pivotal point, lenticular galaxies, noted as S0. At first glance, these galaxies appear as a relatively smooth disk, without clear spiral arms, and with a more or less prominent central bulge. They are sometimes considered as old spirals that have exhausted or ejected their gas, thus halting the formation of new starry arms. In a common scenario, they would have been transformed, through minor interactions or an environment unfavorable to future gas supply, into smoother systems. The lenticular galaxy, with its structure, illustrates well the continuum between sphere, elliptical type, and disk, spiral type. The bulge, often massive, resembles a ball of old stars, while the disk is less gassy, more faded, devoid of detailed arms. Astronomers study lenticulars closely to trace the mechanisms of transition. How can an active galaxy, with intense episodes of starbirth, gradually lose its gas and become, in the eyes of the observer, an S0? This question overlaps with crucial issues about the evolution of matter, the galactic environment, and even the possibility of past mergers. Opposite to ellipticals visually, spiral galaxies occupy the right branch of the Hubble sequence. There are two main categories: unbarred spirals, noted as S, a spherical structure or slight elongation for the bulge, then a disk with spiral arms, and barred spirals, noted as SB, whose central bulge extends into a linear bar from which the spiral arms unfold. The Milky Way, our galaxy, is now considered an example of a barred spiral, with its central bar and arms. These galaxies are generally characterized by a significant amount of gas, hydrogen, helium, plus a variable proportion of heavier elements, which fuels a notable rate of star formation, especially along their arms, where the gas compresses locally. The more regular the disk and the more marked the arms, the more it's referred to as a grand design spiral, meaning a spiral with well-defined regular arms, sometimes extending over tens of thousands of light years. Astronomers adore these complex structures because they reflect the orbital dynamics of the disk, resulting from multiple resonances and interactions with the dark matter halo. When Edwin Hubble proposed his tuning fork diagram, the idea was to arrange galaxies according to their appearance, as if elliptical systems evolved into increasingly open spirals. In fact, elliptical galaxies, E, were placed at one end, and moving to the right, we found tight spirals, SA, then medium, SB, and finally loose, SC. Simultaneously, on the lower branch of the fork, there were barred spirals, SBA, SBB, SBC. The lenticulars S0 were situated at the junction. However, in retrospect, we now know that this representation is more a classification tool than a real evolutionary path. Not all galaxies necessarily transition from an elliptical to a spiral stage. In reality, galactic evolution involves collisions, mergers, gains, or losses of gas, without always corresponding to a progressive movement in the diagram. Nonetheless, the Hubble sequence remains a simple and effective language for describing the basic morphology of a galaxy. Today, with the rise of new technologies, including the James Webb Space Telescope, astronomers refine these categories and sometimes discover cases with blurry boundaries. Some systems, especially in the distant universe, do not fit well with classifications established for nearby galaxies. Early gravitational interactions, differences in gas content, or even the presence of transient bars give rise to unexpected shapes. For this reason, we sometimes talk about a phenotypic update. The Hubble scheme, while useful, must expand to account for a growing morphological variety, revealed in part by the infrared sensitivity of the James Webb Space Telescope. To deepen the understanding of galactic families, astronomers use another concept complementary to purely morphological classification: the main sequence of star formation. This term is sometimes confusing. It's not about the main sequence of stars, like the Hertzsprung-Russell diagram that classifies stars. It is rather a diagram where we compare the total stellar mass of a galaxy to its star formation rate. In other words, how many stars are born, expressed in solar masses per year. In this space, most galaxies form a general band. The more massive they are, the more they generate a high number of stars. This correlation is called the main sequence of star-forming galaxies. However, some galaxies have a very low or even zero star formation rate for their mass. These are called passive or quiescent galaxies. Elliptical galaxies typically fall into this category since they form very few new stars, if any. On the contrary, spiral galaxies are most often aligned with the main sequence as long as they retain a sufficiently dense gas disk to sustain star formation. Occasionally, we come across a hyperactive galaxy, forming stars at an extraordinary rate. These are described as starbursts. When examining Zhúlóng, one finds it has a quiescent central bulge, meaning a core populated by older stars, already reddened by age, contrasting with a disk still active in star formation. This indicates that, according to observations, this galaxy lies on the outskirts of the purely main sequence category. It is not entirely passive since its disk creates stars at a moderate rate, estimated at about 66 solar masses per year, but it is also not as vigorous as some starbursts in the young universe. Some researchers consider Zhúlóng to be on the hinge between massively forming galaxies and already aging galaxies. Morphologically, it clearly falls into the branch of spirals, thanks to its ordered arms. But if one relies on the age distribution of its stellar populations, its bulge could resemble a miniature elliptical galaxy, or the central region of a lenticular. This ambivalence makes it valuable for understanding inside-out growth mechanisms, meaning a scenario in which the core, bulge, forms and runs dry first, while activity persists in the more external disk. As we cross the boundaries of Zhúlóng and gradually move away from this exceptional spiral galaxy, the view broadens to the incredible cosmic panorama surrounding it. This vast scenery, often called the cosmic web, refers to the immense web formed by matter on a large scale, where galaxies, galaxy clusters, and even larger superclusters are organized under the influence of gravity. To understand this web, one must delve into the notion of the macroscopic architecture of the universe and discover how superclusters, filaments, and voids are distributed. To fully grasp what the term cosmic web encompasses, it's helpful to imagine a gigantic mesh, invisible to the naked eye but perceptible in modern astronomical surveys. The universe is not uniformly populated with matter. On the contrary, it features large voids, meaning areas where the density of galaxies is very low, and elongated filaments, where a large portion of the matter is concentrated. Among these filaments, one also finds superclusters, which are dense regions where multiple galaxy clusters come together. This structure of crisscrossing filaments develops more or less massive nodes. In some of these nodes, massive galaxies assemble and influence their environment. To visualize superclusters, imagine a vast field of galaxies separated by luminous highways that would be these filaments, like a celestial organizational chart. The superclusters, even larger, act as concentrations of several galaxy clusters, sometimes containing thousands or even tens of thousands of galaxies. The voids, on the other hand, are like immense bubbles with diameters that can reach hundreds of millions of light years, where matter is extremely sparse. Without a map, a cosmic traveler entering such a void could travel billions of kilometers without encountering a single star, nor even the smallest cloud of gas. In this grandiose mesh, each galaxy is not isolated. It interacts with its surroundings through streams of gas matter exchanges, and gravitational influences. Massive spirals like Zhúlóng in particular play a crucial role as metal factories, meaning they produce elements heavier than helium. These metals, produced in the cores of stars and dispersed into space by supernovae, the explosion at the end of life of certain stars, gradually enrich the surrounding environment with elements necessary for the formation of rocky planets and, potentially, the emergence of life. When a galaxy like Zhúlóng forms many stars, each of them contributes, at the moment of its death, to spreading these elements into the interstellar and sometimes intergalactic space. To understand why these massive galaxies are key in the distribution of these metals, one must consider how stellar winds and supernova explosions eject matter into the galactic halo, a gigantic envelope of matter surrounding a galaxy. From there, these elements can transfer into the intergalactic medium, that is, the space between galaxies. The filaments, which are already rich in baryonic matter, can then transport these materials to other galaxies or circulate them on even larger scales. Simulations suggest that this process of chemical enrichment occurs continuously, progressively favoring the emergence of increasingly complex structures and the possibility of forming planets dense in minerals. For now, the actual amount of metals distributed in this way remains challenging to measure precisely, but large observation campaigns, coupled with high-sensitivity spectroscopes, are beginning to establish a more complete map of the chemical composition of galaxies and their halos. To verify these hypotheses and refine the models, astronomers and cosmologists use very advanced numerical simulation programs, among which is the famous Illustrious-TNG suite. This simulation is designed to recreate on the scale of a large piece of the universe the evolution of matter, taking into account numerous physical phenomena: gravity, fluid dynamics, star formation, the impact of supernovae and supermassive black holes, as well as the emission and absorption of radiation. The results of Illustrious-TNG can be compared to observational surveys, like those from the James Webb Telescope, to see if the distribution and assembly of galaxies match what is predicted by theory. Researchers particularly focus on how massive spiral galaxies form and fit into the virtual cosmic web of Illustrious-TNG. They observe, for instance, whether these galaxies are mainly located in dense material nodes at the junction of multiple filaments, or whether some flourish along the filaments in more modest regions. Comparisons of density, size, star formation rate, and molecular gas proportion are part of the validation criteria. If the simulations manage to faithfully recreate an object similar to Zhúlóng, it would mean that the physical and cosmological ingredients incorporated in the simulation are likely on the right track. Conversely, if no galaxy resembles Zhúlóng, or if it appears in a completely different context, it may be necessary to review the hypotheses or refine the simulation parameters. In this sense, Zhúlóng acts almost like a cosmic testbed. It is a concrete, well-studied example of an early heavy spiral that allows us to test the robustness of our galactic formation scenarios. Today, it is understood that for a massive galaxy to emerge so early in the universe's history, there probably needed to be a rapid and sustained input of cold gas. Gas at temperatures around a few thousand degrees Celsius, for example around 10,000 Celsius, rather than the millions of degrees Celsius of gases heated in halos or in shocks. This gas flows along the filaments of the cosmic web and enters the galactic disk, fueling the formation of new stars. In the early phases of the universe, this gas supply chain had to be both continuous and efficient to explain the appearance of large spirals. Simulations, including Illustrious-TNG, incorporate such gas flows and observe how the density of the intergalactic medium varies over time. They show that the filaments are richer and denser in those distant times, which can accelerate the growth of certain galaxies. Beyond simple star formation, the identity of a spiral galaxy also results from the distribution of angular momentum. For a grand disk to form and wind up, the rotational motion must not be too disturbed. This largely depends on the mergers experienced by the galaxy. Major collisions tend to create elliptical or very chaotic galaxies, whereas more gradual material contributions allow the disk to develop and organize into spiral arms. The case of Zhúlóng and cosmic reality is intriguing. How could it maintain such a harmonious spiral appearance when the universe was still young and marked by frequent disturbances and collisions? This is precisely where the comparison with simulations like illustrious TNG becomes fascinating. We seek to trace similar trajectories to see if Zhúlóng is a unique object or the representative of a broader class of early galaxies. In this vast ensemble, there is also the question of where Zhúlóng is situated in relation to superclusters or galaxy groups of its time, and what the intermediate environment between clusters and filaments looks like. According to initial indications, the location of Zhúlóng would correspond to a moderately dense zone of the cosmic web. It is not an overcrowded supercluster core that could have jostled it, nor a complete void. Astronomers suspect a vein of gas still present, nourishing star formation, but not to the point of saturating the galaxy. Spectroscopic observations, i.e., the detailed analysis of the light emitted by the galaxy, allowing the deduction of its chemical composition and dynamics, should confirm or refute the presence of these gas flows. Along the timeline, we are about 1.2 to 1.3 billion years after the Big Bang, when the distribution of matter begins to clearly manifest filamentous structures, although different from those we see today nearly 13.8 billion years later. As the universe has grown, the cosmic web has stretched, while the filaments have thickened or thinned depending on the expansion of space. Major current superclusters, like the Virgo supercluster to which our Milky Way belongs, were probably in their infancy. Zhúlóng itself was located in one of these embryonic superclusters or in a transitional region, possibly absorbing matter flowing from less dense regions. This configuration, as sought to be replicated in simulation, involves identifying in illustrious TNG a halo of equivalent or even greater mass, equipped with an active disk and capable of attracting enough gas. It is a complex mission, as one must virtually scan all the galaxies formed in the simulation at ZWST 5.2, which corresponds to the time of Zhúlóng, a redshift of about 5. From the perspective of galactic chemistry, Zhúlóng's position within the cosmic web holds crucial importance. Within the filaments, the matter already contains elements synthesized by the first generations of stars, albeit in small proportions. But a galaxy the size of Zhúlóng, with its sustained star formation, about 66 solar masses per year, can become a veritable hub of enrichment. The more it accumulates gas and forms stars, the more it produces heavy elements ejected into the disk, then potentially into surrounding areas. It can be expected that, in the millions of years that follow, these elements will be found within a radius of several tens, or even hundreds of thousands, of light years. It's a considerable zone of chemical influence. Simulations are essential to visualize this dispersion. By linking the speed of stellar winds and jets, possibly originating from black holes, we can estimate the distance beyond which significant enrichment occurs. Later, other satellites or passing galaxies could take up some of these metals and continue to weave chemical links in the cosmic web. This distribution of elements is also accompanied by the propagation of heat and radiation. However, even in the early universe, ambient temperatures in the intergalactic medium generally measure in the tens of thousands of degrees Celsius. They are higher in halos or shock fronts and drop in less dense areas. If a figure were needed, the cosmic microwave background at this time was a few tens of degrees above absolute zero. As an illustration, at a redshift Z/5, the temperature of the background could be around 370 degrees Celsius. But the gas in the filaments can be considerably hotter, especially if it's shocked or compressed. For example, a filament may have certain segments where the gas is close to 10,000 degrees Celsius, while other pockets do not exceed a few hundred or thousand degrees Celsius. This thermal balance, coupled with the dynamics of accretion, determines the rate of star formation in galaxies like Zhúlóng. In addition to helping understand the evolution of Zhúlóng, studying the cosmic web allows predicting how such a galaxy will fit over billions of years into the dynamics of its supercluster. We know, for example, that over time, spiral galaxies tend, in an increasingly dense environment, to merge with each other or to get absorbed into enormous clusters dominated by large elliptical galaxies. The play of gravity over colossal durations is inescapable. Over several billion years, many collisions occur, reshaping the form and configuration of galaxies. For Zhúlóng, located in a time where the universe is young, the probability of future transformations is very high. Simulations allow one to surmise what the probable fate of such a galaxy might be. Could it remain spiral for a long time, or would it become a large elliptical through the absorption of satellite galaxies? This will depend on the local density, the number of neighbors, the activity of its black hole, feedback, and multiple other factors. If we place this in an even broader perspective, the history of Zhúlóng becomes a link among others in the construction of the superclusters of the distant future. Superclusters are immense groupings that can contain several thousand galaxy clusters. Ours, named the Laniakea supercluster, includes the local group, of which the Milky Way is part, and extends over more than 500 million light-years. Let's take a dive among our cosmic neighbors. Let's start with the Milky Way itself. From Earth, we perceive its whitish glow streaking across the celestial vault like a milky ribbon. The term Milky Way actually comes from this impression of milk spilled across the firmament. But if we could position ourselves above the galactic plane for a top-down view, we would clearly distinguish a barred spiral galaxy. This designation means that, from the center, rather than a simple spherical core, we observe a bar-shaped structure stretching over several thousand light-years. Astronomers estimate that the Milky Way extends about 100,000 light-years in diameter, although precise measurements can vary depending on the technique used to observe the most distant stars. A light-year corresponds to the distance light travels in a year, which is about 10 trillion kilometers, a number beyond comprehension. To give a sense of scale, traveling at the speed of light, about 300,000 kilometers per second, would take us a century to cover 100 light-years. So, traveling across the Milky Way in its entirety is almost the magic of science fiction. One of the key features of the Milky Way is its central bar. It's not solid like a metal bar. It's an elongated concentration of stars, gas, and dust, forming a luminous bridge across the galactic nucleus. This bar is denser at the center and tapers towards its ends. Astronomers believe that the presence of a bar indicates a certain stage of maturity in the life of a spiral galaxy. More precisely, it would result from angular momentum reorganizations in the galaxy's disk. Over time, this bar acts as an internal engine that redirects and concentrates gas towards the center, sometimes fueling new star formation or, in other galaxies, the activity of a central supermassive black hole. In the case of the Milky Way, most of the star formation activity is situated in its arms, while the core, or bulge, remains relatively older. However, infrared measurements have repeatedly shown that this bar does exist and that it influences the overall geometry of the galaxy. Just beyond the bar, we find the central bulge, which can take on a particular shape, often compared to a peanut when viewed edge-on. This is an intriguing feature. Instead of being just a spherical bulge, this bulge has a somewhat elongated shape, with a protrusion appearing to spread across two lobes, particularly visible in infrared surveys. Why this shape? Scientists suggest that the central bar, by oscillating and rotating, can cause large amounts of stars to move up and down from the galactic plane, creating this peanut silhouette when observed from the side. This is referred to as a box-shaped peanut bulge to highlight this appearance. It is estimated that the stars in this region are rather old, sometimes over 10 billion years. This makes it a rich laboratory for studying the history of the Milky Way, as old stars retain a chemical trace of the past universe, like cosmic archives. Astronomers typically measure the metallicity, i.e., the amount of elements heavier than hydrogen and helium, of these stars to gradually reconstruct the formation of this bulge. As we move away from the center, we reach the spiral arms of the Milky Way. Our galaxy officially has several distinct arms, such as the Perseus arm and the Sagittarius arm, connected by a bar structure. However, among these arms, one is more modest, and we call it the Orion arm, or sometimes the local arm, because this is where our solar system resides. This arm is not the most massive nor the most spectacular, but for us, it is undoubtedly the most important, since it is our cosmic address. The Orion arm stretches over thousands of light years and encompasses our star, the Sun. On a human scale, the Sun seems isolated in space, but in reality, it is part of a gigantic gathering of hundreds of billions of stars scattered throughout the galaxy. Spiral arms are not rigid. They are density waves where stars and gas clouds manage to condense and pull each other along. Think of them as stellar traffic jams. Stars temporarily concentrate in denser areas and then disperse. Thanks to this phenomenon, we can distinguish well-defined arms in many spiral galaxies. Within these arms, episodes of star formation frequently occur, revealed by clusters of young, hot, and luminous stars. Some of these very hot stars could reach several tens of thousands of degrees Celsius on their surface as they evolve in thick regions of gas and dust. In the Orion arm, we also find many iconic exploration sites, such as the famous Orion Nebula itself. Now, let's leave the Milky Way for a moment to look outward toward its most well-known neighbors, M31, the Andromeda Galaxy, and M33, the Triangulum Galaxy. Both are part of the local group, a collection of about 50 galaxies, mostly dwarf galaxies, of which the Milky Way is an important member. M31, often referred to as the Milky Way's big sister, is visible from the northern hemisphere of Earth as a small fuzzy patch to the naked eye when you know where to look in the constellation Andromeda. Located about 2.5 million light-years from us, it is slightly larger in diameter than the Milky Way and probably comparable, or even a bit superior, in the number of stars. Sometimes estimates change over the course of observations as we refine our measurement techniques, but it is thought that Andromeda might harbor between a few 100 billion and over 1 trillion stars. Just like the Milky Way, M31 is a barred spiral galaxy, although the shape and strength of its bar remain a topic of debate. In any case, extensive studies indicate that it presents a prominent central bulge and vast arms where star formation is active at different times. Modern telescopes have mapped entire regions of Andromeda, identifying immense gas clouds, clusters of ancient stars, and ring structures, perhaps resulting from past collisions with smaller galaxies. As for M33, the Triangulum galaxy, it is more modest than its two big sisters, but that does not diminish the fascination it evokes. M33 is also located in the local group, just under 3 million light-years from Earth, not far from the general direction of Andromeda. It is considered an intermediate or late spiral galaxy. Its spiral structure may appear less pronounced, and its bulge is less imposing. Some research suggests that it does not have a very strong bar or that it possesses a very discrete one. Nevertheless, M33 exhibits intense star-forming regions, which make it bright in radio or infrared waves. Many nebulae filled with nascent stars have been discovered there, and it is a prime observation ground for studying the processes of starbirth in a medium-sized galaxy. Additionally, M33 is often considered an accessible prototype of a galaxy undergoing active evolution, bridging the gap between large, massive spirals and the smaller galaxies of the local group. The fact that M31, M33, and the Milky Way are relatively close to each other on a cosmic scale creates a collective environment where they can weakly interact. Dwarf galaxies also orbit around these giants. Astronomers study tidal tails, bridges of gas or stars that can appear when two galaxies approach or even brush past each other. In the case of M31 and the Milky Way, large-scale gravitational interactions, though weak at this time, will become much more significant in the future as they continue to get closer. We now arrive at one of the most remarkable points regarding the future history of the Milky Way, its inevitable encounter with Andromeda. Current measurements, particularly those by the European Space Agency's Gaia satellite, which catalogs with great precision the position and movement of over 1 billion stars in the Milky Way, indicate that M31 is approaching us at a speed of about 100 kilometers per second. Even though this may seem fast on a galactic scale, it is a very slow process. It is estimated that this encounter will culminate in about 4 billion years. Yes, it is difficult to conceive. The entire duration of Earth's existence is only about 4.5 billion years, and life on our planet has developed during just a fraction of this immense timescale. Yet, for galaxies, billions of years represent a completely usual duration regarding their evolution and interactions. At the time of the merger, the Milky Way and M31 will begin a true cosmic ballet. Their halos of dark matter, invisible but massive, will overlap, and countless stars will start to intersect. There is a very low probability of direct collisions between stars. The void is so vast that two stars have a slim chance of crashing into each other. On the other hand, clouds of gas will collide more strongly, causing intense bursts of star formation in some regions, while other areas may be displaced or distorted. Ultimately, after several passages and interactions, the two galaxies will merge to form a large entity, probably elliptical or lenticular in type. Computer simulations suggest that once the merger is complete, the new galaxy will have lost the typical spiral structure, at least according to classic collision scenarios. Spirals tend to transform into large ellipticals following major mergers, as the internal dynamics of the disks are disrupted and the orbits of the stars become more randomly distributed. That said, significant uncertainties remain. The presence of bars, the initial alignment quality between the Milky Way and Andromeda, the amount of available gas, and many other factors can influence the final morphology. Despite these uncertainties, the astrophysical consensus remains that, in a few billion years, our galaxy will have a very different appearance from what we know today. What relevance does this future event have concerning the broader question of the study of early spirals? In reality, observing the future merger of the Milky Way and M31 provides us with a model of what a collision between two major spirals may look like, even if it unfolds over immense timescales that exceed the human lifespan. As we discover in the distant universe already massive and fused spiral galaxies, we wonder about the mechanics that could have led to these forms so early in cosmic history. The anticipation of the merger between the Milky Way and M31, with the dynamics that accompany it, can serve as a reference to compare different galactic assembly scenarios. In the distant past, it is possible that ancient spirals met under specific conditions, leading either to the formation of mixed structures, more regular galaxies, or even giant spheroids. By studying what awaits us in 4 billion years, we better understand what may have happened 10 or 12 billion years ago when the universe was only a fraction of its current age. Everything responds like an echo through time. What we observe here and now can serve as a guide to dissect phenomena now extinct or unobservable directly. Spiral galaxies have long fascinated astronomers and sky enthusiasts because their beautifully extended arms shimmering with billions of stars seem to embody cosmic harmony. We are now going to explore one of the most captivating aspects of these structures, their potential link to life. We will see why the spiral arms often provide particularly conducive environments for the formation of stars rich in heavy elements, how supernovae influence the balance between radiation and the birth of new stars, and finally, we will dive into the field of exobiology to understand the hypotheses made about the possibility of habitable worlds nestled in very distant spiral galaxies from the first billion years of the universe. It is essential to remember that in astronomy, the term metal does not only refer to what we call iron or copper in everyday life, but includes all elements heavier than helium. Thus, oxygen, carbon, nitrogen, or silicon are considered metals in the vocabulary of astrophysicists. This way of speaking comes from the predominance of hydrogen and helium in the universe. All other elements, even if they are non-metallic from a chemical point of view, are grouped under a single term. The amount of metals in a star or galaxy is called metallicity. The higher it is, the more likely it is that rocky planets similar to Earth will form, as silicate, iron, and other heavy elements are needed to create a solid planetary core, and complex organic compounds, essential for the emergence of life as we know it. So, what makes the spiral arms so interesting for the emergence of these metals and ultimately for the emergence of life? It is all related to the dynamics of the spirals themselves. The arms remain visible thanks to density waves that compress the gas and interstellar dust in specific locations of the galactic disk. Where the gas is thus slowed down and concentrated, new waves of star formation are triggered. In a young spiral galaxy, particularly those emerging in the primordial cosmos, a moderate to intense pace of star creation is observed. Each of these stars, especially the most massive ones, will produce various heavy elements during their existence and end of life. Researchers have therefore found that the spiral arms are active stellar nurseries, privileged locations where stars are born, enriching the environment with metals. Chronologically, in the first hundreds of millions of years following the formation of a spiral galaxy, it is especially the massive stars that eventually explode as supernovae. These supernovae scatter heavy elements in the interstellar medium. The result is a local and progressive increase in metallicity, thus a favorable environment for the formation of potential rocky planets the size of Earth or even larger. Let us now delve into the details of the role played by supernovae. When a massive star, typically much larger than our Sun, sometimes 8 times more massive or even more, exhausts its nuclear fuel, it collapses abruptly on itself in an implosion that rebounds as an explosion. This is a supernova. These extreme events can reach temperatures of several 100 million degrees Celsius, propelling gigantic quantities of enriched matter into space. Iron, nickel, oxygen, carbon, neon, magnesium, and many other elements disperse into the surrounding gas. These explosions also contribute to the emission of a burst of very high energy radiation, sometimes visible at phenomenal distances, and play a crucial role in the balance between the overall luminosity of the spiral arm and the amount of gas remaining to form new stars. If the rate of supernova A is too high, the intense radiation and violent shocks associated could sterilize nascent planetary environments. But conversely, if there are not enough supernovae, the gas will not be sufficiently mixed or enriched in metals, and there will be a lack of indispensable ingredients for building planets conducive to life. Therefore, a delicate balance is required. This dynamic between creation and destruction, sometimes referred to as the cycle of interstellar matter, directly influences the potential emergence of habitable planetary systems. It is noted that the position of a stellar system within the spiral arms can significantly affect the viability of a hypothetical biosphere. Indeed, the probability of being subjected to the negative influence of supernova explosions decreases as one moves away from regions of intense, massive star formation. The central areas of a spiral arm, where very massive stars are born, can be subject to a series of catastrophic events on a planetary scale: violent stellar winds, intense radiation, or multiple gravitational disturbances. Meanwhile, stars located a bit further back, in less dense sectors, can benefit from more stability. Thus, one could imagine that in a spiral galaxy, regions moderately charged with gas, neither too close nor too far from the arm's core, offer an ideal compromise between metal input and the relative tranquility necessary for complex organic chemistry. This galactic habitable zone is a concept already applied in a very general way to our own Milky Way. It is assumed that being thousands of light years away from the galactic center while remaining in the disk is an asset for the emergence of life, as it benefits from the disk's metal density without being exposed to the high activity of the central core. This idea can be transposed to distant spirals, even if their structure, age, and formation history differ. By studying the specific episode of the earliest spiral galaxies, it is observed that metallicity could still be relatively low compared to more recent galaxies like ours. However, if these galaxies had a high efficiency in converting baryonic gas into stars from the first giga-years, billions of years, then this process could have occurred more rapidly than expected. Successive supernovae could have quickly seeded the surrounding space. It is therefore conceivable that, in certain regions of these galaxies, rocky planets may have formed relatively early in the history of the universe, perhaps earlier than commonly imagined. This observation has led some exobiologists to wonder if life may have appeared elsewhere, outside our local sphere, much earlier than on Earth. For us, who are familiar with the idea that life took its time to develop in the Milky Way, this hypothesis may seem bold. Yet, nothing seems to formally prohibit it, provided that the environmental conditions, supernova rate, metal enrichment, gravitational stability, were met. Of course, the question remains, how would living organisms, or even prebiotic structures, withstand the violent transformations of a young and dynamic galaxy? The first billions of years of the universe were marked by more frequent galactic collisions, more intense quasar jets, and a context of cosmic reionization, where energetic photons roamed freely through intergalactic spaces. In an early spiral galaxy, these challenges might be even more pronounced if the galaxy is undergoing interactions or if massive star formation is sustained. Nevertheless, life, at least as we know it, does not settle overnight. Light years separate the early stages of heavy star formation and the formation of habitable planets, followed by even more time for biological processes to begin on the surface or in an ocean of one of these planets. It is generally agreed that if life has a chance to develop somewhere, it requires time and a relatively stable chemical environment. Consequently, a spiral could offer a certain regularity in the distribution of gas and the rhythm of supernovae compared to an irregular galaxy or one in the chaos of a merger. Even in these very ancient galaxies, the existence of stable niches is not entirely to be excluded. When we talk about exobiology in this context, we envision potentially very diverse forms of life. On Earth, the central element of life's chemistry is carbon, capable of forming complex molecular chains surrounded by oxygen, nitrogen, hydrogen, sulfur, and phosphorus. For this type of chemistry to take root, there must at least be a planet where these elements are abundantly available. In the spiral arms of the first galaxies, the rapid multiplication of supernovae could distribute these key atoms, but also generate harmful radiation. This does not mean that life cannot exist. Earth itself experienced intense bombardments over 4 billion years ago, yet prebiotic chemistry thrived. Perhaps in some early spiral galaxies, low radiation zones, such as protected interstellar clouds or inside thick gas envelopes, could have served as cocoons for prebiotic chemistry. These isolated environments could have contributed to the formation of complex molecules, and, given the presence of a sufficiently stable star, a protective atmosphere or boiling oceans, a primitive biosphere might have emerged. Another important aspect is the lifespan of medium-sized stars, comparable to the Sun. Unlike massive stars, destined for brief and violent existences, stars of moderate or low mass burn their nuclear fuel more slowly, offering a longer period of stability. On Earth, the emergence of life as we know it seems to have required several 100 million years, during which molecular chemistry and biological evolution could take their course. In a spiral galaxy, the chemical mixing performed by the arms can furthermore redistribute these medium-mass stars throughout the disk, while maintaining a steady flow of new massive stars that fuel, through their supernovae, the production of metals. Thus, in an early spiral arm, we might have simultaneity. On one side, recent supernovae injecting metals into the environment, and on the other, a reservoir of older, calmer stars around which stable planets could form. This relative cohesion between stellar formation and aging is one of the drivers of exobiological interest in these rotating disks. Of course, for now, this is only hypothetical. Modern telescopes are beginning to provide us with more precise and deeper observations. Thanks to their instruments, we can study the chemical composition of distant spiral galaxies. Indeed, we detect the presence of oxygen, carbon, or other signatures that attest to the abundance of heavy elements necessary for life processes. The challenge lies in determining if these elements are present in sufficient quantities and in what proportions. For instance, the presence of carbon and oxygen in a spiral arm does not automatically mean that a biosphere has been established. It mostly demonstrates that there are physico-chemical conditions conducive to the synthesis of organic bases. Subsequently, additional factors would be needed, such as the presence of liquid water, a suitable atmosphere, a mild temperature, a few tens of degrees Celsius more or less, and sufficient time for complexity to develop. This entire chain of events, extremely contingent, is at the heart of modern exobiological research. A frequently raised question is that of temporality. In the early spiral galaxies, the activity was sometimes more tumultuous than in a mature-aged spiral galaxy, because dark matter and galactic halos were being structured, and intergalactic gas streams could pour into the disk, occasionally leading to bursts of star formation episodes. Each of these bursts induced a peak of supernovae a few million years later. Thus, we find ourselves facing a pattern where, over short periods, a region could experience an avalanche of massive star explosions. On Earth, repeated catastrophic events, such as asteroid collisions or bursts of radiation, are considered constraints that can be fatal to life. But paradoxically, they can also serve as catalysts for evolutionary changes. By analogy, in a distant spiral arm, consecutive shocks could have similar effects, dismantling emerging biological structures, or conversely, reorganizing the protoplanetary disk around an average-sized star, contributing to chemical diversification. Not having access to the precise history of these so distant galaxies, we can only conjecture about the exact consequences of these sequences of events. Nevertheless, the fact that we already perceive signatures of notable metallicity there shows that the raw material is present so that, at least, the chemical recipe for life may potentially be assembled at some point.